There exist convenient design equations for fatigue with both alternating and mean stresses that apply to solid round shafts. So if we consider a typical shaft application where the only source of tau is torque, and that torque maybe has an alternating and a mean component, well, then we're going to have a mean torque, which is going to be a mean shear stress, which is 16 times the mean torque over pi d cubed. And we're going to have an alternating, which is 16 times the alternating component of the torque times pi d cubed. Now, often there is no alternating component of the torque, but there could be torque pulsations. Now, for a shaft, if there is no axial loading, the only source of sigma, the only source of normal stress, is going to be transverse loads which cause bending moments, for example, from gears. And then you're going to have a mean sigma, which is going to be 32 times the mean bending moment over pi d cubed. And you're going to have an alternating normal stress, which is going to be 32 times the alternating component of the bending moment divided by pi d cubed. Again, with no axial loading. All right. Now, fatigue safety factor, SE SUT over sigma A prime SUT plus sigma M prime SE. These are von Mises. Okay, for combined loading. I can rewrite this equation as 1 over sigma A prime over SE plus mean von Mises stress over SUT. Now, if I look at equations 655 and 656 from topic 4c, sigma A prime, I've got to apply stress concentration factor to sigma A nominal. I got to square that, and I'm going to have plus 3 times tau squared in the von Mises, except now I'm going to have 3 times the shear stress concentration factor times my tau squared, and all that's under the square root. Okay, and then similarly I'll have sigma M prime. I'm going to have a stress concentration factor times the mean stress squared. I'm going to have a plus 3, going to have KFS times the mean tau, all squared, all to the 1/2. Okay, and if I substitute in these expressions for sigma A and M, tau A and M from above, I'm going to get sigma A prime. Okay, big old square root, underneath of which I have KF times sigma A, which is 32 times MA over pi d cubed. And that's going to be all squared. And then I've got a 3, and I've got a KFS times my sigma, which is, let's see, sigma was 16 times the torque, 16 times TA over pi d cubed. And that's all squared. That's a fine mess, but if I want to pull out 32 over pi d cubed here, I can make that 32 over 2, make this 3 over 4. If I have 32 over 2 in here, 2 squared is 4, bring that 4 outside, and now I can pull out 32 over pi d cubed from both of these terms, giving me sigma A prime equals 32 over pi d cubed. It's squared in both of these terms. When I pull it out of the square root, it becomes just 32 over pi d cubed. And under the square root, I'm left with kf times ma, all squared. And 3/4 times kfs, the shear stress concentration factor, times my alternating torque, all squared. And then similarly, just changing the subscripts, I'll get expression for sigma m prime. It'll have the same 32 over pi d cubed on the outside, and then I'll have kf times the mean bending moment squared plus 3/4 of kfs times the mean torque all squared. Now I can substitute those expressions into the safety factor equation. You see sigma a prime and sigma m prime there. So if I do that, NF, I'll go back to the blue. I think it reproduces a little better. Okay, so what's NF? I got 1 over, alright, gigantic fraction line thingy there, sigma a prime over SE. And so the sigma a prime, 32 over pi d cubed. What's on the bottom here anyway? I got sigma a prime and a sigma m prime. They're both going to have a 32 over pi d cubed. So I can take that out right away. Now I had, for the alternating, I had kf times ma all squared plus a 3/4 kfs times alternating torque all squared. So that was the sigma a prime. That's got to go over SE like that. Okay, and then I've got to add the term corresponding to the mean stress, kf mm squared plus 3/4 kfs times tm all squared. And that was over SUT. Alright. So ultimately, it'd be nice if I could just solve for the diameter, right? Given the safety factor, given the mean and alternating torques and bending moments, given my stress concentration factors, can I just solve for the diameter? Well, if I pull this up above here, I'm going to end up with pi d cubed over 32 on the top. Let's see, d cubed. D cubed is going to be 32 nf over pi times all this mess on the bottom. So d is going to be the cubed root of that. Alright, so we'll write out the final result there. D is equal to, giant curly braces, 32 nf over pi outside of giant square braces, or square brackets. I got the kf ma squared plus 3/4 kfs ta all squared over SE plus, I got a kf times the mean moment squared plus a 3/4 kfs times the mean torque squared. And that was all over SUT. And this is all going to be to the power of 1/3. Okay, let me take that, bring it over here, running out of space. Okay, so I got to close my square brackets. I got to do my giant curly braces, and it's all to the power of 1/3. So once again, that is only for solid round shafts with no axial loading. So the thing about this equation, though, you still are probably going to need to do some iteration. The SE corrected is going to be a function of the diameter through the size factor, and these stress concentration factors, Kf and Kfs, they're going to be dependent on the diameter as well. So you'll need to maybe guess values of size factor and stress concentration factors up front. Solve for D. Use that D to update the stress concentration factors and the size factor. Resolve for D. Check the new values of Kf, Kfs, and SE until you achieve convergence.